In part 1 of this video, we learned how to tell if something is a metallic bond, an ionic bond, or a covalent bond. Next, we are going to now use this information to help name various compounds. So if I give you the chemical formula of a compound, we're going to learn how to name it. But the first step to that is identifying the type of bond or the type of compound that we have. So we have to understand this stuff that was covered in part 1 before we can move on to this part 2 stuff. So watch part one if you haven't already. So naming rules. I'm breaking this down as simply as I can. Let's start with a polyatomic ion bonded to another polyatomic ion. These are probably my favorite to do because they are the simplest to do. All we are going to do is we are going to write down the name of the first compound and then write down the name of the second compound. That's all there is to do. We don't have to change anything. We don't have to add anything. Nothing else. We just have to identify what polyatomic ion is this and what polyatomic ion is this. We don't even have to count how many of each one we have. So this 2 is irrelevant for how we're going to name this. So we have, at this point, we should have our polyatomic ions memorized. We recognize that this right here, NH4, is ammonium. So I'm going to write down ammonium. Next, I recognize CO3. That is carbonate. So I'm going to write down carbonate. All right, now that I wrote down the first polyatomic ion and the second polyatomic ion, I have now solved the question. That is, ammonium carbonate is the answer to what NH42CO3 is. So we are not using prefixes. We are not using the IDE ending. We're just writing down what polyatomic ions we have, and that's all we do for these. So those are my favorite. Next, really just as simple, we have a metal bonded to a polyatomic ion. So the polyatomic ion is still the second part of the word. So here, it's really going to be pretty much the same rules as that previous question. We are going to write down the name of that metal and then the name of the polyatomic ion, and that is all we are going to do. So again, no prefixes, no IDE ending. So we're going to identify this. We have potassium here. We have potassium. And we have SO4 is sulfate. So potassium sulfate. We have identified the first element and the second compound, and we have now solved this question. Potassium sulfate. That's all it is. Next, things are going to get slightly more complicated, but still incredibly reasonable. We have a polyatomic ion bonded to a nonmetal. How do we name this? Well, we are going to still not use prefixes. We are never using prefixes for ionic compounds. That is one of our rules. For ionic compounds, no prefixes, almost ever. Never in this class, at least. And then we are going to do one small extra thing here, and we are going to replace the ending of the second element with IDE. So let's try that. We have our first compound, the polyatomic ion. NH4 we recognize is ammonium. So we are going to write down ammonium. Next, that second part of that compound, that element right there is chlorine. But we are going to replace the ending, or let's write down what we have. So we have Cl is chlorine. But we have to abide by this second rule that we have here. We're going to replace the ending of the second element with IDE. So let's take off this ending, INE. Let's delete that and replace it with IDE. Anytime the second element ends in a non-metal, we are going to replace the ending with IDE. Every time the second element ends in a non-metal, we are going to replace the ending with IDE. So keep that in mind going forward. And that is for ionic and covalent bonds. Anytime the second element ends in a non-metal, we are going to replace the ending with IDE. All right, so ammonium chloride was our answer to that one. Next, we have a metal bonded to a nonmetal. So still an ionic compound, so no prefixes. And then we are going to replace the ending of the second element with IDE. So really pretty similar to that last question that we just solved. So here we've identified this is right here is calcium. Ca is calcium, so I'm going to write that down. And then F is fluorine. So I'm going to write that down. And then take a guess as to what I'm going to do next. Well, we are going to abide by this rule right here and replace the ending of the second element with IDE. Fluorine is a nonmetal. It is the second part of our chemical compound. Therefore, we are always going to replace that ending with IDE. So let's do that. Calcium fluoride is our answer. CaF2 is calcium fluoride. All right, next example. Now we're going to have a transition metal bonded to a polyatomic ion. So still involving an ionic compound. This is going to form an ionic compound. But instead of just a regular metal, we're going to use a transition metal and see what difference we have there. So what we're going to do is we're going to write down the name of the first element, and then we're going to put a Roman numeral after it, and then the name of the second compound. So the difference is when we have a transition metal, and this is something else important to note, every time we have a transition metal, there is always a Roman numeral written after it. So let's try that out. Again, this is an ionic compound, so no prefixes. But the difference here between here and what we did previously is we are going to include a Roman numeral after that transition metal. So here we have Fe2CO3 3. So let's write down what we have. We have iron, and we have carbonate. But I'm going to leave a space here so that I have room to write my Roman numeral. Since the second element ends in a polyatomic ion, we do not need to replace the ending with IDE. We just leave it as is. That's only if it ends in a nonmetal. So if iron blank carbonate, we now need to figure out what we need to write right here in this blank. What Roman numeral goes there? Let's figure that out. So the first thing we know is that the Roman numerals for this right here, anytime we're involving a transition metal, it's going to be a number between 1 and 6. So it's always between 1 and 6. The charges never go higher than 6, and 6 is pretty rare. It's usually between 1 and 4. Next, let's figure out exactly. So now we have it narrowed down to like a 16% guess, or whatever that is, 1/6. But we can narrow it down a little bit further because there's something else that it's always not. And I really want to take some time to point this out. A lot of people think that if we have a number written out here, the Roman numeral is just that number. but I'm going to write that in red because this is so wrong, and we don't ever want to make this mistake. A lot of people think that this number is the Roman numeral, and that is absolutely not the case. That is not the Roman numeral. So we have now narrowed it down to, it is a number between 1 and 6 that is not 2. So we now have a 20% chance of getting this right, because we have a 1 in 5 chance of getting it right. It's a number between 1 and 6 that is not 2. So it's either 1, 3, 4, 5, or 6. So let's make sure we are never, ever making this mistake. If there is a number written right here, that is not what's going to go in the Roman numeral. So guess something else, because there is a 100% chance you're going to get the question wrong if you put this number as a Roman numeral right here. That is not the answer. All right, let's try learning how to solve this. So what this Roman numeral actually is the charge of iron. It is the charge of the element before it. So iron, the reason why we have to have this Roman numeral is because iron can form multiple charges. Sometimes it forms a positive 2 charge, and sometimes it forms a positive 3 charge. And we need to figure out which charge this iron has. And we need to describe that as a Roman numeral right after the iron. So let's look into it. So iron has, like I said, either a positive 2 or positive 3 charge, but we don't even have to know that much. What we do know, though, is that CO3, that is carbonate, and we should know the charge that carbonate has. So CO3, we know that carbonate always has a negative 2 charge. All right, and iron, you might know that it sometimes has a positive 2 charge, sometimes has a positive 3 charge, or we don't even have to know that much. We can figure out what charge it has. All right, so we can see right here, there is no number written right here. That tells us that there is no charge. This element, or this compound rather, has no overall charge. So even though carbonate has a negative 2 charge, iron, whatever iron's charge is going to balance out this negative 2 charge to give a total charge of the compound of 0. That's what we have determined by nothing being written right here. So let's figure out how we can do that. The simplest method for this particular example is what I like to call the reverse crisscross method. And there's kind of a shortcut to solving this, and I'll show you that, and then I'll kind of prove it up here. So the shortcut is, if I have a 2 written right here next to the iron, I'm going to take that 2 and I'm going to write it up here. And next, if I have a 3 written next to the other element, I'm going to take that number and write it right here. What if this wasn't a 3? What if there was no number in there? Well, then I would put a 1 right here, and the charge would be 1 for iron. But we have a 3 written there, so I'm going to write, so that 3, I'm going to put up there. So like we said, carbonate has a negative 2 charge. So I'm going to actually write that in the same color we just drew that arrow in. So we know that this negative 2 came from this 2 that was written next to the iron. Next, we have that 3, and that 3 is going to be what is right here. And that 3 can tell us that iron is going to have a positive 3 charge. Obviously, we did not just do this to be confusing. Scientists did not decide that, hey, we're going to make this number right here equal to the number of carbonates that we have. That's not what the rule is. It just kind of happens to work out that that is a shortcut for figuring out what the actual rule is. But yeah, so let's look at the overall point of this up here. So we have two carbons. We have two irons, designated by this 2 right here. And then we also have 3 carbonates, described by this 3 right here. So what we're going to do is we're going to take this 2 and say we have 2 positive 3 charges. So we have an overall charge here of positive 6. Next, we have 3 negative 2 charges. So we have an overall charge here of negative 6. So the overall charge for this atom is 0, which is exactly in line with what we have here because we had nothing written there telling us that there's no charge there. So obviously this method is a little bit more confusing, but it always works, and it helps describe why we are doing this crissity-crossy thing. We are, it's just a shortcut for this a little bit more confusing, more mathematical approach. But this more confusing mathematical approach is actually an easier approach in other problems. And let's look at that on the next one. But what we determined here through this reverse crisscross method is that we write this 2 right here, tells us that the carbonate has a negative 2 charge, which we already knew because we have the charge of carbonate memorized. And then the iron has a positive 3 charge. That caused everything to balance out to an overall charge of 0. And so what is going to be written here in this space after the transition metal is the charge of iron. So this has been a very long and roundabout way of saying that this positive 3 right here is going to be what is written right here as a Roman numeral representing the charge of iron. So iron 3 carbonate is our answer. All right, let's try another example. Now, instead of a transition metal bonded to a polyatomic ion, we're going to have a transition metal bonded to a nonmetal. So, a lot of the same rules. This is an ionic compound, so no prefixes. It's involving a transition metal, so we are going to put a Roman numeral after the first element that represents its charge. And then but since the last element is a nonmetal, we're going to replace the ending with IDE. So we're going to look at our periodic table and we recognize that we have copper here. And since copper is a transition metal, we're going to leave a little space to put the charge of copper right there as a Roman numeral. And then we have oxygen right here, so I'm going to write oxygen. All right, the second element, though, we are going to replace the ending with IDE. So let's do that here. Instead of oxygen, we're going to write oxide. And let's now worry about what the charge of copper is. Notice that we don't have any numbers right here. So we can't just take the number here and write it here, and number right here and write it right here, because there are no numbers. We have to have numbers in order to do that. So let's think about what we will do. Well, let's look at what we know. So we know that copper has the ability to form multiple charges. It's a transition metal. Transition metals are weird. They can form multiple charges. But oxygen, not a transition metal. Oxygen always forms a negative 2 charge. So let's write this up here. Oxygen always forms a negative 2 charge because it's in column 6. It needs to gain 2 electrons to get to 8. And if it gains 2 electrons, it gains 2 negative charges and it ends with a negative 2 charge. All right. Next, so we know that oxygen forms a negative 2 charge, but this compound doesn't have a charge written here. That means this compound is uncharged. So we know that oxygen forms a -2 charge, but the overall charge here is 0. So we need to figure out what charge copper has now. So what -2 equals 0 is the question. So we have copper, and we do not know what charge goes there. We don't know. But we can figure it out through a little bit of math. What -2 equals 0? Well, any number minus itself is going to equal 0. So 2 minus 2 equals 0. So that tells us that copper, and I'll write it in a different color for us. So this +2 is where we get this 2 that I'm going to write right here. So copper has a +2 charge because it is bonded to oxygen, which we know has a -2 charge. And we only needed 1 copper to balance that out because there's no number written here. So that tells us there's only 1 copper and 1 oxygen. So copper 2 oxide is our answer to this. All right, we have one final scenario, except for acids, which I'm going to cover in a whole nother video. Next, we have a nonmetal bonded to a nonmetal. And this is if this is not including acids, so not including a nonmetal that's starting with hydrogen. So hydrogen bonded to something else. We'll talk about it later. So a nonmetal bonded to a nonmetal. What we're going to do is we are now going to use the almighty prefix, and we're going to be using a lot of prefixes. So we're going to use a prefix plus the first element, plus the prefix, plus the second element, and then we are going to slap that IDE ending on because the second element ends in a nonmetal. So we're always going to use prefixes, always using prefixes, except we are not going to use a prefix for the first element if there is only one of it. We'll see what that means in this example. And then we are going to replace the ending of the second element with IDE because we always do that if the second element is a nonmetal. All right, so CS2 is our example that we're going to solve. So C is carbon, so let's write that down. So we have carbon, and S is sulfur. So I'm going to write down sulfur. But we next need to count how many of each we have. We have 1 carbon, and that's going to fall into our exception. If we only have one of the first element, we are not going to write a prefix. So no prefix written here. However, we have 2 sulfurs, and I'm always writing a prefix for that second element. So I need to think about what the prefix for 2 is. The prefix for 2 is di. So I'm going to write Di. And then lastly, I'm going to replace the ending of the second element with IDE. So instead of disulfur, it is disulfide. Replacing the ending with IDE. So carbon disulfide is our answer to that final question. We have now gone through every single possible scenario of naming compounds involving ionic or covalent bonds, except for acids. Acids will be covered in a future lesson, so be on the lookout for that video. But hopefully this is helpful for how to name compounds. If you download these notes, it covers every single possible scenario. The trickiest thing are the transition metals, and we'll just know to use either the crisscross method or balancing the ions to 0 method, and we should be able to solve that every single time too. So hopefully that's helpful. Good luck.